Hi everyone, welcome back to our video tutorial series. We're starting a new topic now where we're going to create fabrication data from our parametric models of surfaces. The first step is to create surface panelizations, which were covered in the last topic. And then from those, we're going to use the data structure of a tree to create some sort of strips of material that we're going to be able to unroll into a flat configuration and then arrange them into a laser cutting template so that we can fabricate a model. So the final objective of this video is to create the fabrication data for something like this, which is a simple translation surface that can be, this can be an architectural element, it could be a house, it could be the top of a courtyard. This material, this structure here, we're going to look at how to do that structure and how to do the paneling and the flat fabrication data for the paneling. So let's jump in. So here we can see the final step of this of today's algorithm. I'm gonna switch over to a shaded view so that we can see here the C-plane and stuff. Here's 0, 0 and stuff. And then I'm just gonna go over this definition, and then I'm gonna recreate it using just recreate it using Grasshopper. There's some parts that I'm not gonna cover, like the attractor for these offsets right there, but it's gonna be pretty good. So as you can see, I'm gonna turn this button on, and what this button does is really cool because it only shows you in Rhino the selected components. So we have our translation surface right here, and then we have the panelization done with a very simple domain segmentation. And these domain segmentation, what it's doing, it's creating these 15 by 28 panels. So what I'm doing is I'm doing 15 on the U direction. As you can see, these are 15 divisions, 1, 2, 3, 4, 5, 6, all the way to 15. And then we have 28 divisions over here. These are 28 on the V direction. So we have those two, right? And then what I'm doing is I'm going over to sets, list, partition list, and that basically, this is a list of surfaces, which are these patches of surface, these trimmed surfaces. And the size of the chunks, this is just a single list. You have like 15 panels, and then you have the next 15 and the next 15, and you have that 28 times. So the N for this list, the number of items, let's just go with the number of items, will actually be 15 by times 28, which is just these divisions here and then these divisions here. So what I'm doing with this component grabs all of that list. This list is just, we can think of it as a box. It has element 0, element 1, etc. And each one of these elements is one of these surface patches, right? So it goes all the way to 15 times 28 will be 420, which so it'll have 419 elements, and that'll be just the final element right here. So that's the way the list is coming out of this component. And what I'm doing here is using the same slider that I'm using for the V count in the size of the partition list. What partition list does is it takes, you specify a size of a partition, and let's just say it can be 3. So it breaks it down into a tree, and each branch inside the tree will have n equals 3, or in this case 28 elements. So what that means is that out of this panel I can see that I have now data with 15 branches. We have 15 branches, and each branch has 28 elements inside of it. And that's pretty cool. It's important that this should be sort of, it should be an even number, so that every list has the same number of elements inside of it. Okay, so I'm gonna continue constructing that, and I'm just gonna show you, this is the final state for this video, and I'm gonna just continue from this spot. Okay, so I have my chunks here, which is, it's basically a tree that has 28 elements inside of each branch, and you can see here that you have the list here, and you have 28 elements inside of the first list, the first branch, which is this one. This is the branch path for this part, and then this is the branch path for the second branch, which will also have 28 elements, as you can see, and so on and so forth, all the way up to there. If you want to sort of look at this in a more like specific way, you can go to sets, tree, and you can get tree branch, and you can connect a tree, and you need to connect a path here. And that path can be, for example, if I have a panel, and that path is just this text right here, which is curly brackets, 0, semicolon, 0, semicolon, 0, semicolon, 0, curly bracket. And that's kind of the first path right here, and I can connect that there, and as you can see, what I have now, it's the first branch. This is branch with path 0, 0, 0, 0. And these paths, you have a bunch of zeros just because you have a bunch of steps before. You can see that this this list has 3 zeros as the sort of the branch path. And Grasshopper will sort of aggregate these, like as you can see, the previous step, you have only 2 zeros and on the branch path, even though it's a list with a single element. Sort of Grasshopper just sort of always, it's always sort of aggregating the branch paths all the way up to, I think, this one. This is 0, 0, and then for some reason, this will be just the first one, and this is the branch 0. It's kind of the same thing. It's a little bit annoying that Grasshopper does that, but it does it because not every step along the way will have the same branches. As you can see, for example, this component has data with 1 branch going in. It has 1 branch. And it has data with 15 branches going out. So that's the reason that Grasshopper sort of aggregates and repeats these branch path numbers on there. So it's a little bit annoying, but that's the way that you can see it. If you don't want to type this in every time, you can get the branch paths of a tree. If you go to set tree statistics, and what this component will do is it'll give you a list of all the branch paths in the tree. As you can see here, you get the branch paths, you get the number of branches or the length of each branch in the tree, and then the number of branches or branch paths that you have So this component will give you information. This is just information about the tree. It's not necessarily the geometry inside of the tree. So that's what this component does right here. So if I want to get the second or the third or the fourth or whatever branch inside the tree, and I don't want to type, for example, this 00007, for example, to get this branch, I can get this list of paths, and then from that list of paths get the sixth item, you know. So what this will do is this will give me whatever branch path is on that position. These are the branches. So as you can see, if I move this up to if I move this up to 14, you'll see that we have all the branches on the tree, like that, like so. So there we have all the branches, each one of these branches. And let me just show you something. And the reason that we're doing this is that we want to get out of this panelization, we want to get the strips that go on this side. Yeah, we want to get these strips, because those strips are the ones that we're gonna use plugin to unroll them. Okay, so anyways, that's kind of what we're gonna do. So we need to triangulate them. So I'm gonna put this over here because I'm gonna use it in a little while. And what I'm gonna do, we already went through the explanation of that tree. And we're gonna do some things with these tree. Again, this tree has the chunks. It has a branch for each one of these rows of panels. And what we're gonna do is we're gonna go to surface analysis and we're gonna deconstruct BREP. So what this will do, this will give us the faces, the edges, but what we want here is the vertices. And if we connect a panel here, we can see that we have lists that have 4 items inside of them. Each one of these lists corresponds to one of these panels, right? So these panels, what they are is we have one branch inside of this tree for each one of these panels, and you'll see that you have now 2 levels on the tree here, 2 numbers that change. So let me just show you what that looks. So if we do this, if we get the first branch of this tree now, the vertices component, we can see that we get this is the first branch, and it only has these 4 vertices. And yeah, so let's and then we can see that all of these, we can see that we get all of these branches. But what's important here is also that this tree here, you'll see that it has 27 branches, and they all share these 4 zeros. But the next one, it goes back to 1 and 0. And the reason for that is that this tree that's going into this component is already into 28 branches, or sorry, 15 branches. And then inside of that, each one of those lists, we have these panels. So now from this component, we get a new branch inside of that tree that has the vertex list, and we're gonna use that to recreate and triangulate these panels like so. We're gonna make these panels like that. We're gonna sort of create a diagonal between each one of those, and the way to do that is we're gonna get set list item, which is here, list item, and we're gonna connect the vertex list. And as you can see, it selects all of them but these. And what's going on here, it's as though as we're selecting the first item of each branch. And the first item of each branch is basically the first vertex in the vertex list. So it'll be this one. So this will be the vertex 0. If we go and we select index 1, you'll see that we can just get a panel here, or yeah, we can just set multiple numbers. Yeah, let's go right click, set multiple integers, and get the number 1. So we get the 0 and 1 vertices. So we get this one and this one. So that's vertex 1. If we get vertex 2 here, you'll see that it's this one. And if we get vertex 3, you'll see that it's the final one, the last one. Okay, so if we want to build this triangle, we need to create a surface that has 0, 1, and 2 as its vertices. And then we need to create, if we want another triangle that's this one, we need to go from 0 to 3 to 2, as you can see. Or we can go 0 to 2 to 3, etc. Any way you want it. So we need to construct that. We need to sort of construct that. So I'm doing this right now just individually in this one, but I'm going to do that in each one of this. So I'm going to do that in the whole thing. So there's the whole thing. So right now what we have is we have I'm going to set multiple integers, and I'm going to go with 0, 1, and 2. So let's just delete that. And then 0, 1, and 2. And if we do curve, spline, polyline, we can create a polyline from those vertices, as you can see. 0, 1, and 2. Oh, sorry. And we can do a closed polyline. So we go right click on closed, set Boolean to true. And that'll give us this triangle, as you can see right there. So again, if we do the tree analysis tool that we have right here, if we just sort of connect that tree in there, you'll see that each one of these branches has that triangle there. So that's the first triangle that we have. And what we're going to do now is we're going to do the 0, 3, 2 triangle. So I'm going to copy these two. And then I'm going to set multiple integers. And we're going to go 0, 2, and 3. And then we have that. If I do Control Shift, I can just get that here. And as you can see, that's that triangle that we're doing. So we're doing each one of these triangles right there, right? So what we're going to do now is we're going to put this is like the first one, this is like the first one, and this is like the second one for each panel. So we want to create a list or a tree that has this as its first item, then this one, then this one, then this one, then this one. So you can see the pattern emerging there. So we're gonna weave those two lists, and to do that we're gonna go to Sets, List, Weave, and what weave does, it takes two streams, two trees basically, and the pattern is always 0, 1 by default, but you can change that, and it'll take an item from this, and then an item from this, and then an item from this, and then an item from this. And if we again analyze this tree using a little tool here, we can see that this is the first branch, and then that's the second, but we have both triangles in there, right? So so yeah, I think that what I'm gonna do is I'm actually going to do that, but I want to do it with surfaces. I don't think I want to do it with polylines. So I'm going to get surface, freeform, and get the boundary surface from the edges. and that'll be this surface, and then get the boundary surface for these polylines, and that'll be this surface. So we have the both triangles, and then we're going to do this and then this. Okay, so that's great. So now here you'll see that we can go and get this parent viewer, and then we have this data with 420 branches, and as you can see that you have 28 branches, and then it sort of restarts with 28 new panels right here. So we're gonna use something that's called a flattened tree to sort of, we can get a single list. So flattened tree, what this does, it basically creates just one single branch with all the elements in there. So this is a list with all of those surfaces. But you can do that partially. We want to sort of go up one level. So we're going to do tree, shift, paths. And what this does is it basically, it goes back one level. Let me just show you one level into the tree. And as you can see, I now have the whole things right here. These are the strips, and I've constructed them from the data of the surface, like so. And this is important because now what we're going to do is we're going to unroll these surfaces to basically just to get them from a, like, I'm gonna bake this. I'm gonna bake it into Rhino. So now I have it in Rhino, and oh, it's an individual, it's each individual surface. So let me just go back. What I'm gonna do is I'm going to surface brep join, and if everything's joined, let me just bake just one single branch. Oh yeah, sorry, this is not necessary. I think we want to join these guys. Yeah, we want to join them, and then yeah, we want to join these surfaces. We want to join them, and then this branch, these are these two. So yeah, I think we do need the shift paths. Sorry, we do need the shift paths, and then we do need the join. And now this branch now is one single poly surface right there. So what I'm doing here is I'm getting all of these triangular panels into a single tree branch, each one of these rows right there, or columns if you will. Then I'm joining them into a single poly surface, and I baked it just so that you can see it. And as you can see now, I have 15 branches because now I've joined all of these surfaces together. I can actually now flatten this. Let me just disconnect. And if I flatten this, I basically now have, and I bake this, I basically now have 15 different poly surfaces, each one composed of the rows of triangular panels. And I don't know if you know Rhino, but Rhino has this very powerful command that's called unroll surface right there. And unroll surface, what that does, you can do explode no, labels yes. And if you do an unroll with Rhino, what it does, it basically puts a poly surface, it unrolls it, it develops it into a flat configuration on the C-plane so that it's a flat panel. I'm going to do that without the labels. And as you can see, that's a flat panel. And the great thing about this is that it now, you can now laser cut this laser cut the outline of this and engrave on the laser cutter these lines so that you can fold a flat material into a curved configuration like this model that I have right here. So that's what we're doing. We're gonna do that, but we're gonna do that inside of Grasshopper. So to do that, we're gonna use a plugin that's called Open Nest. Open Nest has, it's on Food for Rhino, it's this one. If you have Rhino 7, I think you need to download this version. I don't know if this version will work with Rhino 7. This version is super new, and I think it's really, really, really cool. Consider donating to the developers because it's a really great, and what Open Nest does, it does something called nesting. Nesting is the act of, I don't know if you've ever laser cut something, you know that you have to arrange the pieces in the laser cutting boundary of the machine. So nested, that's called nesting. And Open Nest, it's a plugin that does nesting automatically. So Open Nest, if you correctly install it, and there's a page, you can follow the instructions on Food for Rhino. You can go to Food for Rhino, open, and then just search for Open Nest. And then inside of, and then you get these Open Nest. And then that's the, you log in, you download it, you follow the instructions that are right here. You can also use Package Manager to install it. That's also very good. And once you have that, let me just delete this and, oh, sorry. Yeah, there we go. And then let me just take this out. So now I have everything there. And if you installed it correctly, you now have Open Nest over here. It'll live over here in the Parents tab. And it has this unroll function. This unroll function, it's the same function as the one I just did in Rhino. And you basically plug in the brep and it'll do the unroll function there. The problem with that is that it's the same thing, for example, as doing all of this and then unrolling them. And yeah, well, if you do that for each one of these, it'll put them, they will always be put inside the 0, 0, so you'll have to manually sort of move them around. But really what Open Nest is doing, it's just putting all of them right here. As you can see here, I have 15 joined B-reps. And then out of here, I have 15 unrolled B-reps that are going out of there. And they come out as a tree. I can actually, for example, let me just delete that in Rhino. And I can actually bake them so that you can see what's coming out. And it has all of the pieces there, you know? Okay? So what I'm going to do now is I'm going to, these are now sort of all clumped together. They're all on top of each other, so they're intersecting. So I can't really laser cut these. What I need to do is I need to sort of put them separately inside of the laser cutting boundary area. So I need to do something like this. But this is Grasshopper, this is computational design, and that means that we can do this using the computer to do it automatically so that we don't spend time doing what I'm doing right now, right here. So what I'm going to do is I'm going to grab from Open Nest, I'm going to grab the I'm going to flatten these. You can also get you can also get, I'm going to flatten these, and then I'm going to plug them into the This is the Open Nest engine, the nesting component to arrange them. And I'm going to connect the B-reps to the geometries. And then I'm going to set up, I don't know, I think it's going to be a rectangle as a sheet. And this rectangle will have size 0 to 90, sort of as if it was centimeters. It can be meters or something else. 0 to 60. So that's this rectangle here. It can be a different rectangle. It depends on the boundary of the laser cutter. But you know, the laser cutters here at the university, and many of them have a 900 by 600 millimeters. So I'm going to use that as a sheet. And as you can see, Rhino or Open Nest have already automatically arranged these pieces into the sheet right here, right? So that's a very powerful thing to have. That's a very good thing to have. But now the problem is that we don't know which one of these corresponds to each one on the model. So we need to do some tagging. Well, this is an 8. We need to do some tags. So we're gonna tag each piece. And the way we're gonna do that first in the model, which will be here, then in the unrolled surfaces, which will be here, and then in the nested surfaces, which will be here. So what we have is, this is the model strips. These are the unrolled strips. And then these are the nested strips. At any point in time, you can actually bake and do this manually, but if you want to do it automatically, you can do so. You can actually, for example, if you encounter any problems, what you can do is you can bake all the individual surfaces like so. Let me just turn off Grasshopper, and you can actually manually just join those in Grasshopper, use join in Rhino, sorry, and then unroll those and then put them aside, right? And then you can hide this, and then you can go ahead with the next one. You can join, and then do unroll. Oh, sorry, sorry. Join, unroll, and then it'll do it however it wants. You can hide. I mean, you can do it manually, but it'll take a while. So that's the reason that we're doing this automatically. So those are the nested strips. So we're going to tag each one of them. So for the model strips, what we're going to do is we're going to go to Surface, Analysis, Volume. And we plug in, area. We plug in the B-reps, and it actually gives us a point right here, which is the centroid, okay? And we have 1 point for each one of these. If you have more points, that means that you don't have the shift paths component correctly set up. You might have this, in which case you will have, basically your computer will crash because of Open Nest. Yeah, I had to pause the recording there because it took a while. So what you're seeing now is I didn't use the offset paths, and what's basically going on is that now we have 420 B-reps, which is 1 for each one of these. So what Open Nest is doing, it's unrolling each one of them. And that takes time. It's a computation time. that it's simply just a little bit more. So, and as you can see now, we have one centroid for each one of these. So that's not very good. And so that's the reason that it sort of took a while. So if I plug this back in, like I was saying, that means that we're doing this instead of 420 times, we're doing it just 15 times. So it's a little bit easier for Open Nest to work with that. So anyways, we have 15 centroids, and what we're gonna do is we're gonna use the display tab here, and we're gonna go with dimensions, and we're gonna use a text tag 3D. And this text tag needs a location and a text. And what text are we using? We can use any text, but we're gonna use a sequence series. And we're gonna do as many centroids as we have. Those are the amount of numbers that we need. And we're gonna plug that into text. So as you can see, we have 0, 1, 2, 3, etc. So excellent. So that means that this is strip 0. Yeah. Then you have strip 1, strip 2, etc. So on and so forth. So we have them identified in the model. We're gonna now identify them in the strips, but it's gonna be a little bit harder. So let's do the display text tag 3D, and let's go. It's just the same, basically. It's just the same. These 4 components: the centroid, the list length, and the tag. It's just basically the same. I'm gonna copy them, these 4 right here. But instead of using this, I'm gonna use this brep here, and that gives me just the tags right there. They're all encimadas. They're all sort of one on top of each other, so it's a mess that we cannot even read. But what's good with this is that we're gonna now use another of Open Nest's features, which is this transform matrix, or the transformation data. So what you get out of this is the transformation data to go from the strip over here to the strip over here. Let me turn off everything that's behind. Let me turn just everything back here off. So let me just go preview off. There we go. And let me turn off these, preview off. Yeah, there we go. So we have the unrolled strips and their tags there, and there's a one-to-one correspondence, right? You have strip 0, tag 0, strip 1, tag 1, etc., so on and so forth. So what we're gonna do is we're going to we're going to use the transformation data. And the transformation data is whatever Open Nest is doing to get the strip from here over to here. Open Nest will check the collisions so that they don't. You can change the spacing. For example, if you go with spacing 0.1, you'll see that the strips have 0.1 between them, or you can go with a bigger number, etc. And that just depends on what kind of separation you want between each piece, right? That looks about right. And then the transformation data, it's just in order to get the tag there. What I'm gonna do is I'm going to get the yeah, I can do the same thing. I can get yeah, I can get the, yeah, that's kind of the tag. I can also do this. Yeah, sorry. I can do this without the transformation. I can just get this right here. and that'll be a one-to-one correspondence with my yeah, I have a tag now. I have a tag right there, which is pretty cool. We have the 0, the 1, etc. If you want to check this, you can actually, yeah, you don't need the transform. Sorry about that. If you want to check this, you can just bake the model. And this is 0, right? As we can tell from these tags right there. So that's 0. You can unroll. And you'll see that with 0, we can sort of put it sort of so we can put it sort of on top of this, and you can see that it's actually the same strip right there. So anyways, this is the fabrication data for laser cutting a model like this. On the next video, we're gonna look at how, on the next video, we're gonna look at how to get the substructure. And for your final project, you're gonna have to basically create the parametric model and fabrication data for a project like this one. Okay, so anyways, that's it for today. I hope you liked this video, and I'll see you on the next one.